All right, the shell method, the hardest of the three. Disk method, washer method. Students usually have a decent time with the disk method, and of course you get into washer, and washer can be used for pretty much any problem. You know which problems the washer method cannot be used for? The ones where your teacher says, do this with the shell method. It's a different integral, so they can totally tell which way you did it. And on the AP test, they might ask you a multiple choice question where you have to set it up as a shell. Or they'll be really tricky, and they'll know that everyone likes to use the washer method. So they'll make one of the answer choices like, which of the following is the correct integral for whatever volume? And they'll make the correct choice one that involves shells. So there's ways for teachers and test makers to force you to know the shell method, even though you totally hate it, and even though you can do any problem with washer method that you can do with shell method. Now there are the occasional problem is easier to do with shell method than washer, and vice versa. It just depends on the region a little bit, and I'll get into that in the next video. But pretty much, if you really know what you're doing, you can use washer for any problem that you can use shell for. All right, so what the heck are shells? They should be called tubes. I don't know what happened. It was a bad translation 300 years ago or something, but for some reason every book, every teacher calls these shells, but shell doesn't make any sense. They're tubes. So if you look at this exploded view, you know, in the previous video about disks, I looked at the same sphere shape, right? We estimated a sphere by sort of making it a stack of disks. We sort of stacked up a bunch of disks, and that's the whole point of the disk method. So we take a sphere and turn it into a bunch of flat saucers added together. But guess what? Even though this looks the same, if you pull this apart, it's actually nested tubes. Nested shells. Why are they called shells? Again, I don't know. Shells are what you find on the seashore. These are tubes or pipes. But hopefully you can see from this exploded view that this would really work out. That red tube, or that red rod, because really the red one is solid. It's got an inside diameter of 0, so it basically has no hole. The point is that that is this right here. So here's the red one. And then if you slide the green one up around it, it's a little bit shorter, so the red's going to stick out a little bit on either end. And then the blue is a little bit shorter than the green, so that's why you get this little step right here. And of course the gold, so these colors are identical, and you can kind of see that if you slid all these rings up and just put them one inside of each other, you could imagine sort of sliding them in the right positions so that you create this exact ball shape. How does that help you? Well, that means that theoretically, just like with every other volume problem we've done, theoretically, if you could figure out the volume of each one of these tubes, like the amount of plastic it took to make each one of these pieces of pipe, then if you added up all their volumes, you should be able to get the volume of this sphere. So just like we can calculate the volume of the sphere from adding up a bunch of flat circles, we could figure it out from adding up all the volumes of these nested tubes. Now I know what you're thinking. It's really easy to find the volume of a circle. It's really hard to find the volume of a tube. Who's ever done that before? That's not something you've ever done in geometry or anything. No one's got a volume of a tube formula, but it's going to turn out it's actually pretty straightforward, as I'll show you in a second when we actually introduce the formula. So this is obviously a solid ball. It does not have a hole in the middle. But just like with the washer method, using shells, we can do things that have holes in the middle. So again, we got this bundt cake shape that I first showed you guys in the washer video. And it's got a hole in the middle, obviously, like a bundt cake. And using washers, we just made a stack of discs which had holes in the middle, right? And this drawing, actually, this right here, would look the same whether you used washers or shells. But again, just like with the ball, if you blow this thing up, I actually created this by stacking a bunch of rings inside of each other. So you can see that the little red guy is pretty short, then the blue is taller. And once these are stacked up, the bottom of this shape is flat. Like this bottom surface underneath here is totally flat. So you can see that the red is the shortest, the blue is the longest. That's this guy right here. And then they get short again as we work back taper back towards the center. So the cross section of this shape, we got a bundt over there, and then we got a bundt over there. And here's all our represented rectangles and our rings of our cross sections of our rings, or our shells that we're adding up to the shape. All right. So that's what shells are. Now how the heck we find these volumes? Because as I mentioned a second ago, you've never seen a formula for this before. But here's what's crazy. Now I have a little prop here. My kid's shield. They were making swords and shields the other day. But here it is. So imagine this piece of cardboard is a tube. So you're kind of looking down the center of it. It's pretty, imagine this was perfectly round. That is a tube, right? But what can I do to this? Look at this. If I slit it down the side, so if I just make a knife cut right down there and unfold it, oh my gosh, I have a rectangle. What's the volume of a rectangle? If you make a rectangle, just give it a little bit of thickness so it's not infinitely thin, but it's like a little rectangular slice there. It's just going to be base times height times the thickness. And as we've said in all the other formulas, the thickness is going to be dx, or dy, depending on the problem. But the point is that that little dx or dy, that's the thickness. But now you see why they want to use shells. It's just base times height. It's super simple. There's no r squareds and those pi's in there. It's actually pretty sweet. So the question is, what is the height of this shell? It's pretty obvious that the base, well, if you unfolded it so it's vertical, or unfold it horizontally like this one's drawn here, you can see that the height here is just the height of this little representative rectangle. But what's the base of this thing? Because when I unfold this thing, I actually get a pretty wide strip, right? This drawing isn't quite fair. This thing really unfolds to something more like this shape. This golden thing right here folds to this shape. So we've got h, but what the heck is this giant dimension here? Well, it turns out if I just take the radius of the original ring, so pretend that's the center, this is the radius of the ring, wouldn't this distance down here just be the circumference of the original pipe? Because going from here all the way around, that is the length of the rectangle I ended up with. So if I slit it and open it up, 2 pi r is the length of this bottom edge. And then h is still just h, so that's all good. And then thickness, of course, is dx. So we just found out that the volume of this thing is just simply 2 pi r times dx, which looks pretty similar to the disk and washer formulas. Like the disk formula was pi r squared dx. So the only difference is that instead of having r squared like we did for disks, we just got r to the first power, but then we have 2 pi. So actually what's really great about this method is there's no squared right here. Gone are the days where you have to FOIL out crazy stuff. It's going to introduce a new level of messiness in this r thing. We'll get that in a second. Oops, I forgot h. Ugh. 2 pi r h dx. All right. So that is the formula. That's where it came from, just slitting the tube and opening it up. Let's see how to use these puppies. All right, so as usual, if the integral, if the area or the volume of one little slice or one little shell is 2 pi h r dx, all we have to do probably is integrate that, and we'll end up with the volume of the entire revolved crazy solid. So, sure enough, that's what we're going to get. Now, the question is, I want to point this out right now. I'm going to keep pointing it out again and again, because this is where shells and washers are tricky. I just want to compare shells and washers here for a second. So, with the washer method, if we had a vertical spin axis, that means we have horizontal little rectangles, right? Because if you spun a horizontal rectangle around a vertical thing, you end up with a washer shape, and that's how we ended up with flat washers with holes in the middle. But if you want to make a tube, so that means the vertical spin axis was a dy problem. But if you want to make a tube instead, that means for that same vertical spin axis, same region, you need vertical representative rectangles. Because like if I take this little guy and spin him around, now I've got more of a tube shape. So see how that created, see how a vertical little rectangle and a vertical axis lead to a pipe? Because as you go like this, you end up more of a pie shape, whereas if you go like this, that's how you end up with a flat thing. So that's the key, and the key thing to remember is that for shell method, a vertical axis gives you vertical rectangles, or a vertical axis gives you dx, and a horizontal axis, therefore, is going to give you dy. So it's the switcheroo. Shell method, horizontal spin axis gives you dy, whereas for washers, horizontal spin axis gives you dx. There's little rectangles the other way, so their width is going to be in the dx direction. All right, so all that said, here is our formula. And I just want to point that out before showing you the formula in detail because This is confusing enough on its own. All right, so here's the formula we just derived. My circumference, and therefore the bottom edge of that rectangle, was 2 pi r dx. So that's what we came up with. So what is this thing right here, this h of x? H of x is just the height of each little rectangle, right? So this is the exact same thing we just came up with a second ago, where when we have a rectangle like this, we've got h here, and we got 2 pi r here, and then of course the thickness was the dx. So 2 pi r, and then h. So that's just the area. All this right here is just the area of a rectangle, and then dx is its thickness. But here's where things get either really complicated or really simple, depending on if you look at it right. Here's what's different about the about this from the washer method. So in the washer method, we had r squareds and stuff. But on this, both your functions, both f and g, the top and bottom two curve things that create the region, they both go in h. So you see how we replaced h right here with this thing right here? So of our two letters, h and r, both our functions, g and f, both went into h. And that's just the height of each little rectangle. So h stands for height. And I know some books and some teachers use different letters for the length and stuff, but I would encourage you to just use h because that means height of each little rectangle, which kind of makes sense. So the length of the little rectangle is f of x minus g of x, and we can kind of see that geometrically here, because if you take like this middle rectangle right here, if you want to know how long something is, you just take the y coordinate at the top of it and subtract the y coordinate in the bottom and just get that difference in y coordinates. Well, the y coordinate up here is just f of x. The y coordinate down here is just g of x. So that distance in between there is f of x minus g of x. And that's how we got this. That's just the height of each little rectangle. Now here's what's confusing or simple. This thing right here, the radius, this is where students always get confused. The radius is just x. It's not x squared. It doesn't depend on what f of x and g of x are. It's never a number. It's always just x. Or if you're doing a dy problem, it's y. But it's x or y to the first power. Never a square root, never an exponent. Always, always, always just an x or a y. And then this c is just the coordinate spin axis. So just like in the washer method, if you wanted to spin around something other than the x or y axis, if you want to move that axis to the left or right or move it up or down, we had to sort of put in a c value, the coordinate of that spin axis, just to kind of fudge things to allow for a different radius. But that's just what goes in right here. But the radius is just x or y, and then plus or minus a number. That's all there is to it. If we get into harder problems, we might have a c minus x or c minus y, but it's always x or y to the first power. There's never an exponent in this r portion. So never an exponent within r of x. And that's actually what makes this simple, but also makes it confusing if you're used to the washer method. All right, so let's take an example. Y equals 4 minus 2x. So let's see, that's 1, 2, 3, 4. Y-intercept of 4, and then minus 2, so kind of like this. It's not my best line ever. All right, so 4 minus 2x, x equals 0 is the y-axis. And then y equals 0. Okay, so we're looking at this region right here. Want to revolve it around the y-axis. All right, so this is our spin axis. Make it nice and heavy, put an arrow on it. Put a little squirrely dealy. All right, so there's our region. I want to spin around the y-axis. Now, is this a dx or dy problem is the first thing we're going to ask ourselves. It's dx because in the shell method, the little rectangles are parallel to the spin axis. So my representative rectangle right here is vertical like that, which means its thickness right here is in the dx direction. All right, so that means I'm in a dx problem. All right, so now I've just got my dx formula for shells. Let's take a crack at plugging and chugging. 2 pi. All right, so the limits of integration, since I'm doing dx, I need the limits of the x coordinates. So x seems to go from 0 to 2. That's sort of the width of my region. All right, what is f of x? F of x is the upper curve. That's the line, which is 4 minus 2x. I subtract g of x. G of x is just the bottom edge of the region, which in this case is actually the line y equals 0. That's this guy right here was the bottom. All right, and then x. You notice that's not f or g or anything, that's just x. And then minus c. Now c is the coordinate, the coordinate or the location of the spin axis. But the spin axis is the y-axis, which is x equals 0. So my c is 0 in this case. All right, so does that look like an integral we can handle? It does, right? And this is really nice. There's no exponents anywhere. It's pretty wonderful. Although we are going to have to distribute this in, but we'll end up with an x squared before we integrate, but not the end of the world. All right, so the 0 just goes away. So we've just got 4 minus 2x times x. So we got to FOIL that in. So we get 4x minus 2x squared dx. All right, so that's going to integrate to 2 pi. Integral of 4x is 2x squared minus 2/3 x cubed from 0 to 2. 2 pi. All right, plug in 2. You got 2 times 4 is 8. And then 2 cubed is 8 times 2 is 16. So minus 16/3. So that's 2 pi times 24/3 minus 16/3 is 8/3 for a total of 16 pi. All right, so hopefully that didn't seem too bad. You start with the formula, you plug and chug, and you got to remember this formula. F and G both go in that one set of parentheses together, and then this is always, always, always just x or y. If it's a dx problem, you put an x here. If it's a dy problem, you put a y here. In a minute, we'll see the harder ones where you have to switch x and c, so it'll be c minus x instead of x minus c. But for now, plug and chug like there's no tomorrow. All right, let's take a look at another one. All right, so here's one that's pretty similar. The only difference is it's going to have a hole in the middle, because check out our region. So we got y equals 4 minus x, which is 1, 2, 3, 4. Got a y-intercept of 4, then a slope of -1. So like that. And the spin axis is once again the y-axis, which, as I've alluded to, these will get a little bit more tricky when we start using other spin axes, but for now, just the y-axis again. But then the trick is that the region is not going to go up against the spin axis. It's going to stop at x equals 2. So this is our region from y equals 0, x equals 2, and of course that diagonal line. All right, so just when we're working with the shell method, our representative rectangles go parallel to the spin axis. So I've got vertical representative rectangles for this region, which means, of course, they're in the dx. That width is dx. That's why I'm using the dx version of the formula. So what's up next? It looks like I can just plug and chug, because this line is 4 minus x. It's my function. And everything else is defined. So we got 2 pi times the integral. So what does x cover? Well, in this case, it only goes from 2 to 4. So even though my spin axis is all the way over here, my region is what determines the limits of integration, and that's just from 2 to 4. So f of x is just 4 minus x. And g of x, or the bottom of the region, is once again just that line y equals 0, so that's 0. And same thing will happen over here, because the spin axis is the y-axis. Coordinate is x equals 0, so that's why we have a 0 right here for c. All right, so zeros just go bye-bye. And let's get 2 pi times the integral from 2 to 4 of 4x minus x squared when I distribute in that x. So that's going to be 2 pi times 2x squared minus 1/3 x cubed from 2 to 4. All right, so let's start plugging in. All right, so my upper limit of integration is going to be 2 times 16, so 32, minus 1/3 times 8, so 8/3. Oops, plugged in 2 accidentally right there. My bad. Plug in 4, you got 4 cubed is 64 times thirds. So minus 64 thirds minus, now we plug in our lower limit of integration. 2 squared is 4, times 2 is 8. And 8 thirds. Alright, this might be a kind of a booger as far as the fractions go. 32 minus 8 is 24. And then minus the negative 8 thirds, so negative 64 thirds plus 8 thirds is negative 56 thirds, which equals 2 pi times, gosh, 24 is 72 thirds minus 56 thirds. So that's going to be 2 pi times 72 minus 56 is, I believe, 16 thirds. 32 pi over 3. Seems like a rounder number than it looked like I was going to get a second ago, but hey. Alright, so as you can see, these are kind of time consuming to integrate, so from now on we'll mostly just set them up and not worry about doing the actual integral, because the actual integral is just plug and chug, mostly polynomials, so not a big deal. Alright, so here we got another one. Y equals x and y equals x squared. Once again around the y-axis, but then it won't take too long because we're just setting it up, and then we'll do another couple of axes to show you what happens when we have to put in something for c. So let's draw the region first. We got y equals x, which is a perfectly diagonal line with a slope of 1. Then we got y equals x squared, which is like this. And those intersect at 1, 1. Revolved around the y-axis as the last few we've done have been. I'm kind of hitting this pretty hard on the y-axis because I want to just show you how to plug and chug through these, and it's not that bad. So 2 pi. Now once again, I've got a vertical spin axis, which means I got a vertical represented rectangle. So once I draw that guy in, it's pretty obvious that my width is dx. That's why we're using the dx version of this formula. X goes from 0 to 1 for this little region. Alright, so f of x, that is the upper one, and that is just x, because y equals x is that upper curve, minus g of x is the lower curve here, which is x squared. Alright, now for the y-axis, once again c equals 0. So x minus 0 is just x dx. Alright, I have no doubt that anybody who's gotten this far in calculus can probably integrate this. It's a simple polynomial, distributed in the x, and plug and chug through the definite integral. Alright, so what happens when I spin around x equals negative 1 instead of the y-axis? So that's just right here at negative 1. It's slightly out of proportion because that's positive 1, but got to be able to fit it on the page. So here's our new spin axis. It's at negative 1. So what did that do to anything? Well, it turns out I'm going to use the exact same formula. I'm just going to plug in a different number for c. So once again, all this stuff stays the same. I've got 2 pi times the integral from 0 to 1. Because remember, those limits of integration, those are based only on the region itself, not the spin axis. So whether I spin this given region around negative 1, negative 2, the y-axis, positive 50, negative 16, you name it, no matter what, my limits of integration are 0 to 1, because this region itself just starts at x equals 1, x equals 0, and ends at x equals 1. And then these are the same, so x minus x squared. The only difference is that, remember, this term, sort of when we derived this formula, this was our radius, right? That was sort of like the radius of any given shell. So let's look at our representative rectangle. When that gets revolved around the spin axis, it's going to form a tube like this. So does that make sense? It's going to form like a little piece of pipe or shell or tube or whatever. And what's its radius now? Well, its radius would have been just x. We put when we spun around the y-axis, we just plugged in 0 for x. But didn't our radius just increase by 1? By moving the spin axis from the y-axis, moving to the left 1, we just sort of added 1 to the radius of that tube. And of course, every other tube, similarly, is going to get 1 added to its radius because we shifted this little distance of 1 over to the left. I mean, all the radius is bigger. So that's where minus c comes in. Now you might be wondering, why would we take away c? Well, c is just the actual coordinate, so there's a negative built into it. So the point is you're going to get x plus 1. Whether you look at that as saying, hey, on the original problem I just had x here, but now I've got one more, so one bigger radius is one way to look at this. By moving the spin axis further away from the region, we had to add to the radius, so that's why we added 1. The plug and chug way to look at it is that, hey, c is simply the coordinate of that spin axis, and since that's a negative 1, we really just did x minus our c, which is negative 1. And minus negative 1 ends up being plus 1. So either way you look at it, you're looking at an x plus 1, the radius was increased by 1. Now, what did this do to our integral? Not much. We just now, instead of just distributing it in x, we got a FOIL, so we'll get x times 1. We have to FOIL this together to get a polynomial, but still we're just integrating a polynomial, which is pretty easy stuff, again, once you're this far in calculus. What happens when x equals negative 3 as our spin axis? Well, isn't that just 2 more to the left? It's over here. So again, whether you look at this as being x minus a negative 3, or just x plus 3, because we're adding 3 to the radiuses of all the different tubes. You notice I say radiuses instead of radii? I don't know, for some reason it makes more sense here. Like, radii was never a word that made sense to me. Alright, so we're just going to do plug and chug. Same region, so it's still 0 to 1. Still x minus x squared. The only difference is we're going to do x plus 3. That 3 is just accounting for the fact that we just increased our radius by 3 by shifting the region further away. Because as we increase the radius of each shell, the thing gets bigger and bigger. You move the spin axis further away. My radius looks like it's that big now. If I move the spin axis this direction, it's like, oh, look at that. The thing is now going to be enormous. Every time I move 1 inch, my spin axis 1 inch further away, I add 1 inch to the radius. And dx, of course. All right, pretty solid stuff. Cool. All right, let's take a look at dy. Because, of course, just like in the other two types of problems, discs and washers, you can have dx problems or dy problems. In the shell method, you get dy when you have a horizontal spin axis. Because remember, our spin axis is parallel to our rectangles in the shell method. So if I have a horizontal spin axis, that means I have a horizontal rectangle. And a horizontal rectangle has a thickness of dy, not dx. All right, so let's see what happens. First of all, we always sketch our region. So we got y equals 4 minus 2x. Okay, this is the region we did before. It's pretty much. So 4 minus 2x, go 1, 2, 3, 4. And that intersects the x-axis right here because it's got kind of a steep slope. All right, so that's 4 minus 2x. And then we got y equals 0, which is this right here. And then we got x equals 2. That doesn't make any sense. Let's just do this region right here. I don't know why I put in the x equals 2. That doesn't make a ton of sense. So we'll do this region right here, the whole thing. And if I'm doing that, so I got a horizontal spin axis because we're revolving around the x-axis. So that means I've got horizontal represented rectangles. And therefore my thickness is dy, and that's why I got a dy situation. Okay, so I just plug and chug. 2y. Now the size of this region, for the limits of integration, I need to look at the limits of y since we're doing a dy. And y for this region goes from 0 all the way up to 4. Alright, so f of y and g of y. Now you'll notice that I've actually got a slight situation here because I need to function in terms of y. Since I'm doing dy's, it has to be in terms of y. But this was in terms of x. So I've got to rearrange this equation and solve it for x. So we start out with y equals, that's probably a bad place to work that. Start with, where do I want to work this? Y equals 4 minus 2x. So 2x equals 4 minus y. and therefore x equals 2 minus 1/2 y. So this right-hand thing, which is f, is 2 minus 1/2 y. And then g of y is going to be the left hand of the two curve. It's a little bit more obvious when you have a vertical represent a rectangle. It's just f and g is the top minus the bottom. For a horizontal rectangle like this, it's right minus left. So the right hand end of the little represented rectangles are all riding along that diagonal line, and then the left hand end is riding along this vertical thing of just x equals 0. So this is just minus 0. So that just all goes away. G of y is just 0. And then we've got y. So just like we had x minus c or x plus c or whatever in the dx problems, we got y plus or minus c in this problem, since we're doing dy. So we just get y, and then because the spin axis is 0, it's y equals 0, it's just y minus 0, which is just y. Alright, so we can integrate this. 2 pi 0 to 4 of 2y minus 1/2 y squared dy. So that's 2 pi times y squared minus 1/6 y cubed from 0 to 4, which equals 2 pi times 64. That's not right. Sorry, 16 minus 64/6, which reduces to 32 thirds. So we just get 16, which is 48 thirds, minus 32 thirds is 16 thirds, times 2 is 32 pi over 3. Alright, pretty exciting stuff. Got a little nervous with those sixths. Point is, when we switched from dx to dy and did horizontal rectangles, all the same stuff applies, the problem's the same. And then just like with the washer method, if you're going to put a dy over here and use y on the right-hand edge, you've got to use y everywhere else as well. So what happens when we move the spin axis to -2? Well, just like when we did the previous shell problems, all that is plugging in a c. So we're still going to have 2 pi, still going to have an integral from 0 to 4, still going to have 2y, sorry, that was a later step, still going to have 2 minus 1/2 y as f minus g. The only difference is I'm going to have a y, and then whether you look at it as subtracting a -2, because it's y minus c, so whether you look at it as y minus a -2 or y plus 2, either way you end up with y plus 2. And that's because the spin axis, if here's our region, our spin axis is down here below. So the radiuses of all these different pipes just got increased by 2 because our spin axis is 2 below the x-axis. It's 2, when we did the problem the first time, we got 32 pi over 3. Our radiuses were all 2 less than they are now. So if we actually did this integral, we'd end up with a much bigger number. But point is, now to finish solving it, you'll notice you have a y plus 2 as your radius term, so as our r. So the point is that when you FOIL this out, you're going to get a lot more terms. Instead of just 2y minus 1/2 y squared they have to integrate, you're going to get 2y plus 4 minus 1/2 y squared, etc. So it's a longer, nastier thing, and you should end up with a bigger number, since it's by moving the radius further away, we made it physically larger shape, which should have a much bigger volume. And what happens if we did y minus, spinning it around y equals -5 instead of -2? Again, exact same formula, and we still have the 2 minus 1/2 y, but we just got y plus 5 because now the radius is 5 bigger than it would have been originally when we were just spinning around the x-axis. Alright, so just like with the shell and washer method, things get a little bit more confusing when the spin axis is either above or to the right of the region. And you'll notice what happened is all we did, same formula, except c minus x replaced x minus c. So in the previous problems we just worked, we did x minus c, and of course if your spin axis is to the left of your region, that means it's got a negative coordinate, like it's x equals -3 or -5 or something, and therefore that's a negative c. So we always ended up with x plus a number, because we were sort of augmenting or increasing the radius by a little bit when we move the spin axis to the left or below the region. When the spin axis goes the other side, these get switcherooed, and something very similar happened with the washer method. Instead of having x minus the coordinate spin axis, it's backwards and you get the spin axis coordinate minus x. But basically the same story. Other than that, I would recommend just sort of plugging and chugging at this point. It seems like when I work with students, the way to go is just memorize the fact that, hey, if the spin axis is above or to the right of your region, you just switch them up and you do c minus x instead of x minus c. It seems like that's the easiest way to memorize it and plug and chug through it. If you're sort of like a real go-getter and you're shooting for a 5 on the AP test, then by all means you might want to understand a little bit more and think about it and try and figure out how to like think through it every time. But the whole plugging and chugging and just realizing that if the spin axis is above or to the right, you switch up and do c minus x. That's probably the most straightforward way. Seems like that's what connects the best with students. All right, so let's draw our region and see what happens. So we got y equals root x and x squared, two of my favorite curves. So that's square root of x, and this is x squared. And this point is 1 comma 1, which makes our limits of integration nice and easy. All right, so there's our region. And we're spinning it around x equals 2. All right, so that's over here. So that's x equals 1. Here's x equals 2. Oops, not a very good spin axis. And there's a little curly cue to indicate that's our spin axis. All right, so let's plug and chug, shall we? Right through these things. All right, so we got 2 pi. Limits of integration are defined by the region, and the region now there's a dx problem because we have a vertical spin axis, and therefore we'll have a vertical represented rectangle whose little width is dx. So that's how we get a dx. And x seems to go from 0 and 1 for the region. Now the radiuses of the various pipes throughout this region are going to be different than that, but the limits of integration come only from the region itself, which goes from 0 up to 1. All right, so f of x. Now f of x minus g of x, that's just the height of each little rectangle, right? That's going to be root x minus x squared. And then, because I have the spin axis to the right of my region, I've got c minus x, where c is just the coordinate of this puppy. Spin axis is at x equals 2, so that's 2 is my c. And then just take away x. And just as a reminder, what goes in here is always x or y to the first power. It's never one of your functions. The two functions always go in this first set of parentheses, not the second set of parentheses. All right, so at this point, it's a pretty straightforward integral. It might look kind of ugly because we have a root in there, but that's just really x to the 1/2 power. So you'll get 2 root x. I'll just do that next step of the integration without actually plugging and chugging through the whole thing, just to spare you guys' eyeballs. So we got 2 root x minus x root x is really x to 3/2, just like square root of x was x to the 1/2, minus 2x squared plus x cubed dx. So the point is that when you have a root x times another power of x, you just add the exponents, not the end of the world. And of course you could integrate, plug and chug through this. Since the limits are 0 and 1, it's kind of nice. There shouldn't be even any, there'll be some fractions to worry about, but nothing too crazy. All right, so what happens if the integral had been, or we'd been revolving around x equals 5 instead of x equals 2? No big deal. We got the exact same formula as this step right here. The only difference is we're going to do 5 minus x. So it'll be 2 pi, integral from 0 to 1, square root of x minus x squared, and then 5 minus x, because our c is 5 if our spin axis is x equals 5. And last one, all this stuff comes from the, you'll notice that no matter what my spin axis is, as long as it's a vertical spin axis, this first part of the problem is the same. And this is what's great about this compared to the washer method. With the washer method, if you move the spin axis from one side of the region to the other, not only do you have to mess around with 2 minus x and stuff, but you have all these squareds to worry about. Big R and little r switch places. But you'll notice that on these ones, like this x equals -3 is off to the left here. So I just went to the other side of my region, and yet I've still got square root of x minus x squared. The only difference is that instead of a number minus x, I'm just going to have x plus 3. Because now I'm back to the situation where the spin axis is on like the normal side, the left side of the region, and therefore instead of doing c minus x, I'm back to x minus c. So that's x plus 3. So the cool thing about the shell method is you only have to mess with this. Every problem is the same no matter which spin axis they give you. Everything's the same except for your x plus 3 or x plus c or c minus x or whatever. Just this one set of parentheses is all that changes when you mix up the spin axis. You know, given they're all like the same orientation, vertical or horizontal. All right, same thing when the spin axis is above the region. So once again, got square root of x and x squared revolved around y equals 3, so that's way up here. Now you notice there's a horizontal spin axis, which means my representative rectangles just went sideways on me. They're now like this, which means they're dy's, right? So that's annoying. Not that big a deal. It just means that everywhere I had an x, I now have a y, and then my functions have to be functions of y instead of x. So instead of root x, there's going to be y squared. Just get rid of that altogether. So that's y squared, and then this guy is square root of y. And you can get those just by rearranging, you know, for this one square both sides, for this one square root both sides in order to solve for x for each problem. So now we've got 2 pi. I think I'm ready to integrate. 2 pi is 0 to 1 because y goes from 0 to 1. This region goes from 0 to 1 in both x and y. Alright, so f of x, f of y is just, when we're in y, it's the right-hand one, so that'd be square root of y minus y squared Alright, and then because this spin axis is above, I've got to do c minus y instead of y minus c, which is the one we used for the previous dy problems we did. So c is just that coordinate 3 minus y times dy. And I trust you guys to be able to execute this integral. Just going to be a lot of distributing and partial powers and stuff, just like the last one we did. Alright, so around y equals 7, no big deal. Once again, we've got a spin axis that's in the same orientation as last time, and we're just going from 3 to 7, but we're still above the region, which means we got the exact same deal as usual. Rewrite the problem exactly as it is, rewrite our answer exactly as it is. Only replace that 3 with a 7, because that's where the location of the spin axis goes. And FOIL it out, integrate, and we're done. About 20 minutes from now, right? These are long problems. All right, last one. All this stuff's the same, because the nice thing about these shell problems is they're always the same. The only difference is that because -3 is actually below the axis, it's below the region, which is where we want it, sort of like that's the easier way to do it. We're going to go back to what I showed you earlier in this video, like an hour ago, which is that this is y minus c, so y minus a -3, which is y plus 3. So the point is now the radius is it's just like as if you had spun around the x-axis, except we're adding 3 to it to make it bigger. All right, killer. All right, find the volume of y equals x minus 1 squared, x plus 1 revolved around x equals -2. All right, so this is getting to a funkier region. Let's see. Now that we're masters of shell method, this shouldn't be too bad. X minus 1 squared, that is a parabola has just been shifted 1 to the right. So normally y equals x squared. It's a parabola at the origin. This one is just a parabola at x equals 1. So from there it's going to grow like that. Something like that. Alright, so that point is probably 0, 1. And let's see. And then our other, so that's one function. And then our other function is x plus 1. So that has a y-intercept of 1 and then goes up at a slope of 1. So I think this point is 3, comma 4, but we can double check that. The way you get this is just by setting the two functions equal to each other. So set x plus 1 equal to x minus 1 squared. What might be easier is just to guess and see if you're right. So this clearly works for both. And if you plug in 2, or you plug in 3 into both functions, 3 minus 1 is 2 squared is 4, and then 3 plus 1 is also 4. So 3 comma 4 works for both functions, which means that's point of intersection. All right, so there you go. And what are we revolving this around? X equals negative 2. So that's over here. All right, so that's our curly Q. All right, so we want to use the shell method on this. Now, this is actually a great problem to show you when you'd want to use the shell method versus the disk method. If I draw my rectangles like this for the shell method, so obviously the represented rectangle is parallel to the spin axis. But it turns out that I really should be using a vertical rectangles for this particular region. Regardless of whether it's spun around a vertical or horizontal axis, this region is just easier to do with vertical rectangles. I talked about this a little bit in a dx versus dy video in the find the area between curves chapter before this, but I want the rectangle to work for my entire region. You'll notice no matter where I draw a vertical rectangle, one end of it, within this region, one end of the rectangle is going to have its end on the diagonal line, and the other end is going to be on this parabola. So no matter where you are in this region, the top and bottom sort of bounds stay the same. But if I did sideways rectangles, down here, both ends of the rectangle lie on the parabola, but then up here, one end lies on the parabola and one end lies on the diagonal line. So if I wanted to use horizontal rectangles, and therefore the washer method, I would have to split this into two regions. I'd have to integrate the volume of this bottom part, then I'd have to add to that the integral, find the volume of this upper thing. So it's two separate washer problems. But if you skip the washers and just do shells, it's one easy shot, because no matter where I go, my upper and lower ends of the little rectangles are defined by the line in the parabola. So we can just set it up. That means, so I want to do vertical rectangles which have widths of dx, which means I'm doing the dx version of this problem. So I've got 2 pi times the integral from, I'm doing dx, and it looks like this goes from 0 to 3. All right, so I got the top function, which is x plus 1. And subtract the bottom function, which is x minus 1 squared. And then x equals negative 2, so I'm just going to add 2 to x. So x, this is my x minus c situation, which will be x plus 2 dx. All right, so that is the integral. Just pretend I'm spinning around the y and then plug in 2 for c. So this was x minus negative 2, because negative 2 is the coordinate of that spin axis. All right, and then x equals 5. Now that's slightly different, right? So in this first problem we worked, the spin axis was to the left of the region. Now it's going to be to the right of the region, so I got to switch this from x plus 2, x plus c, to c minus x, which will just, so that just means this will end up being a 5 minus x. But everything else will be the same. So all this stuff will be the same, this stuff is all the same. I'm just doing a 5 minus x. What if I had done around x equals 0, or the y-axis? Well, then everything still the same. It's just x plus 0 or whatever. There's nothing there, because when I spin around an axis, x or y-axis, c equals 0, no offset, so we just have x. All right, good stuff. All right, so last one we'll do, we'll just set up a region with 4 different spin axes and see how it goes. So the volume of x equals y squared, that's just that guy again, and x equals 4. Let's see, so this is going to go down here. Because x equals y squared is that whole parabola, not just the top half. So our region is this entire sort of end of a parabola. And spin axis x equals negative 2 for the first one. All right, so when x equals negative 2, That's a vertical spin axis, so I'm going to have vertical represented rectangles. So that's a dx problem. So I'll have 2 pi. X goes from 0 to 4 for this region. And then I'll need, now this is a subtlety. I need to put everything in terms of x, right? Because I need f of x and g of x if I'm using dx. I was given this as a function of y though, so I've got to solve it. So I got to take x equals y squared and solve it for y. So I get y equals plus or minus root x. Now this is really weird, but bear with me for a second. The reason it's plus or minus root x is the top is the plus root x, and the bottom is negative root x. And you'd actually know that from pre-calculus, just because root x is only the top part, is only the top arc, it's not the bottom. And that's because of this. The reason in pre-calculus you never talked about the bottom half is because that's not a function anymore. If you include both the top and the bottom, you fail the vertical line test, so it's not a function, so that's why you never use it very often. But in this case, we're working stuff where we need to use both, so we're gonna have to deal with it. So the top function is square root of x, and then we subtract, so it's f minus g, right? F minus g is the formula. So that means square root of x minus the bottom formula, which is negative square root of x. So those are going to cancel and give us root x plus root x. And then, because that spin axis is the left, it's going to be x plus 2, and then of course dx. So those two root x's combine to give you 2 root x times x plus 2 dx. Now at this point we're just going to have to distribute this in, so we'll get 2x to the 3 halves plus 4x to the 1 half, integrate it, etc. But I just wanted to show you guys the main thing, which is that this is our r. So the two curves, if you will, went here and here, then we just got x plus 2 for r. So what happens if I move the spin axis, still vertical, but I move it to x equals 5, which is right here? Well, if I've told you anything, it's that nothing changes, right? It's exactly the same. The only difference is that because I moved from the left side to the right side, and my spin axis was on the left for the previous problem, but now we're moving it to the right side, instead of x plus a number, it's going to be a number minus x, and that number is 5, because that's our spin axis. So 5 minus x goes right here. All right, so for this last part of the problem, we're going to be dealing with horizontal spin axes, y equals negative 3 and y equals 2. So we're going to have to switch things up a little bit. Now everything's going to be in terms of y squared again, which is kind of where we started. X equals y squared is actually perfect for this. So we're just going to use the dy version. Our representative rectangles are now going to be horizontal, because we have a horizontal spin axis of y equals negative 3. So we got 2 pi. Now what's the range of y coordinates of this region? Well, they go from negative 2 to positive 2. Just because at this point, if you plug in 4 for x, you'll get negative 2 or positive 2 for y. Alright, so we need the right-hand function minus left-hand function. So what determines, if you look at this little representative rectangle, that one end is riding along this curve right here, which is just x equals 4. So our f is actually just 4, and then minus g, which is the parabola, which is y squared. Alright, and then our radius is pretty simple because the spin axis is below the region, which means it's just going to be y plus whatever that coordinate is, which is 3. It's actually y minus a negative 3, which gives you y plus 3 dy. And then if we've learned anything by now, it's that when we move the spin axis above the region, all you do, don't change anything. All we're going to do is just switch up this y plus 3 to instead be the new spin axis, which is up here at 2, which is actually comes in right there at the corner. So when this is our spin axis, it's above the region, so we're just going to do that coordinate, which is 2, because it's y equals 2, minus y. Alright, so this has been the longest video I've ever shot. I think we're coming in near an hour now. But that's the way it goes with shell method. It's just super hard, super confusing. Maybe one of the reasons that so many students are confused when their teachers teach this is that teachers don't have 4 hours to teach you something. It's like they're going to have to pack in shell and washer method into one day, the same as they plugged in U-sub to one day. But I guarantee you the U-substitution chapter is a lot shorter. It takes less time and it's less confusing than this stuff is. So that's why when I tutor this, shell method is the most confusing thing any student's pretty much ever seen. And that's why this video is so long, but hopefully you get the hang of it now. And honestly, if I was you, knowing what I know now looking back, I would try and be an expert in shell method just because it seems like it's easier to execute most of the time than the washer method. So even though most students prefer washer because they saw it first, if you just sort of draw in your representative rectangle, do F minus G and stuff, my personal feeling is that the shell method is actually faster than the washer method if you know what you're doing, which is obviously, it's not always the case when you're first learning this stuff out for the first time.